Hello. So now we'll calculate the work done by the gas in case of adiabatic process. So if you remember, the ideal gas equation was of this format, PV to the power gamma is constant. This was the format of one of the format of ideal gas equation. And when we talk about work done for closed system, we have a formula dWg is equals to PV. So small work done by gas in case of a closed system is represented by PdV. Okay. So this is my equation. Let's say this constant is K. I'll calculate this value later on. So if you want to calculate the work done, we have to replace either the volume or the pressure, and it's easy to replace the pressure here. So this dWg, we can write it as in pressure. In place of pressure, I can write K times of K divided by V to the power gamma dV. Or dWg will become K times of dV upon V to the power gamma. So now you see we have only two variables, volume and work done, W. So let's integrate this function. And if we integrate this function, if I integrate this function from V1 to V2, V1 and V2 are the volume at state 1 and state 2. So it will be equals to, Wg is equals to K times of, if I integrate this function, we'll get 1 minus gamma 1 upon V to the power gamma minus 1 from V1 to V2. Okay. So let's put the limits here. If I put the limit, Wg will be equals to K times of 1 minus gamma 1 upon V2 gamma minus 1 upon V1 gamma minus 1. This is your work done. But here you are seeing this K, we have to replace this value of K. Okay. So let's say this is equation 1 before simplifying it. So PV to the power gamma is equals to K. So what we do, let's put the state 1 and state 2 in this equation. State 1, the pressure is P1 and the volume is P2. So at state 1, if I put the value, it will be P1 V1 to the power gamma is K, and that will be same at state 2 also. It will be P2 V2 to the power gamma. Okay, and that both of these values are equals to K. So let's from equation 1, what I'm doing, this work done will be equals to 1 upon 1 minus gamma, and I'm multiplying this K inside. So it will be K upon V to the power gamma minus 1 minus of K upon V1 to the power gamma minus 1. So now what I will do, I'll replace the value of K. So what I'll do, this K I'll replace by this value, and this K I'll replace by this value. So 1 minus 1 upon gamma. So let's replace the value of K from here. It will be P2 V2 to the power gamma divided by V to the power gamma minus 1, and minus of P1 V1 to the power gamma divided by V1 to the power gamma minus 1. Okay. So we have replaced the value of K. This is equals to Wg. On simplifying, this V2 and V2, if you see, here it is V to the power gamma and here it is V to the power gamma minus 1. So this whole value will convert into P2 V2 minus P1 V1. That is your work done by the gas in case of adiabatic process. So this value, this work done is in terms of pressure and volume. And if you remember, we generally tend to calculate each and everything, whether it is work done or change in internal energy or the heat given, in terms of temperature, if it is possible. So here also we can do the same thing. So if you see the ideal gas equation, if I put the state 1 and state 2 in ideal gas equation, since state 1 and 2, they will satisfy the ideal gas equation also. So if I put the value, it will be P1 V1 to the power nR T1. Similarly, P2 V2 to the power nR T2. So PV is equals to nRT, that's the ideal gas equation, and what I did, I put the state 1 is P1 V1 and T1, and state 2, which is P2 V2 and T2 in ideal gas equation. So this is the equation we are getting. So let's replace the value of P2 V2 and P1 V1 here. So dW will be equals to 1 upon gamma minus 1, oh sorry, it is not gamma minus 1, it is 1 minus gamma. In case of P2 V2, I can write nR T2 minus nR T1. We can get this nR outside. So dWg is equals to nR 1 minus gamma T2 minus T1. Okay. This is one number of mole. If the number of moles are 1 mole, we'll place the value of n as 1 there. So now you can see we are having two formulas for work done, one in terms of pressure and volume and other in terms of temperature. Okay, so this is the work done. So if I convert this equation in differential format, so dWg, I can write it as, if the temperature difference is very small, nR 1 minus gamma dt also. So this is also the equation. This is also the equation for adiabatic process for work done. And this equation we can use further to calculate if the temperature difference is given. If we are having the temperature difference, we can calculate the work done directly out of it. Okay. So now you can see we are getting the work done. We have got the work done in terms of temperature. Work done in terms of temperature difference. And if you remember, if we go for calculating the internal energy, so we have an internal energy formula. And that formula, internal energy formula, differential formula, that is independent of the process. So internal energy, if you calculate, the internal energy of any gas is equals to NCV dt. Or we can say it is NFR dt by 2. That is the internal energy. For any process, the internal energy in terms of temperature is also known. And now we know the work done in terms of temperature change also. Okay. So one more time, let's go for it. So this was the equation for ideal gas equation, adiabatic process, and we wanted to calculate the work done. So what we did, we replaced the value of pressure here, and upon integration, we got this value. This was the work done by the gas in case of adiabatic process. Okay. So upon replacing the value of P2 V2 and P1 V1 from ideal gas equation, we get the work done in terms of temperature difference also, and that was a differential equation. And there is a fixed equation for change in internal energy, that also in terms of temperature. Now we have the work done in case of adiabatic process in terms of temperature. Okay. Thank you.